Thank you very much. First, I want to start by wishing IPENZ a happy 100th anniversary, and I'm very honored to have been invited, to be the speaker at this anniversary. What I was planning to do today is basically 50 years ago, we started on a quest of exploring the solar system using robots. And since that time, we have visited every planet in our solar system, and we gained a lot of knowledge, about the space surrounding us. So what I was going to do is to tell you about the challenges and the excitement of exploration. Why do we explore? What have we learned so far? And what are our plans for the future? But before I do that, I want to tell you how honored I am to be here in Wellington, the home of Sir William Pickering. As was mentioned earlier, Bill Pickering, I think you have this. Basically, we consider him as the founder of robotic exploration of the planetary system. He was the director of JPL in the late 50s to the mid 70s, and that was the early part of space exploration. And he was so honored in the US that the first American satellite, after Sputnik was launched, within 90 days, we launched the American satellite called Explorer 1. And as you can see on the slide to your left, you see Bill Pickering completely on your left, holding the model of Explorer 1. On the right is von Braun, who was coming from Germany, who built part of the rocket. And in the middle is von Allen, who had a scientific instrument on that satellite. And that basically started the era of space exploration in the United States, particularly planetary exploration. On the slide to your right, or part to your right, you see it says Caltech satellite. Caltech is a university in California, which actually manages the Jet Propulsion Lab. And both Bill Pickering and myself, we were professors, or we are still, in my case, I'm still a professor, at the university. And he was very honored. He was twice on the front cover of the Time magazine. So he really represented New Zealand in the best way that you can represent it as an explorer. And then one thing which is interesting, which happened now, kind of put the bookends for the Dr. Pickering time. Before he retired, he launched the Voyager spacecraft. That was 36 years ago. And that Voyager spacecraft is the one which flew by all the outer planets, by Jupiter, Saturn, Uranus, and Neptune. And recently, a few months ago, it actually passed beyond our solar system. So this is the first human object over the human history which actually have gone beyond our solar system. And now it's traveling between the stars, in a sense. So it's going into the interstellar medium. And one thing unique about it, other than the scientific aspect, you see that golden disk. So at that time, people were thinking, well, what happened if alien, sometime in the future, alien civilization will pick that spacecraft? How do we explain to them who we are? And what that disk has on it is a collection of pictures, of our planet, of people on our planet, and basically to send a message to neighboring civilization of what we are all about. Now, this was put on disk because that was launched in the 70s. Many of the young people here wouldn't have any idea what a disk is, but my generation know what a disk is. Now you just put it on a stick and you put it in your computer, and that's all the memory you need. But that's kind of a message to other neighboring civilization, if ever, they capture that spacecraft. So let me go back and explain to you, why do we explore? People will say, why do we spend all that money? Of course, we are human, we are curious about exploring. But let me tell you how I describe it, in general. I would say about 13 billion years ago, we know there was a Big Bang. Now, don't ask me after what was before the Big Bang. I have no idea what was before it. But we believe that actually there was a Big Bang, and an enormous amount of particles were created. And then somehow those particles got together and they formed galaxies and stars. And this is a perfect example of a collection of galaxies. Now, you need to know that there is billions and billions of galaxies in our universe. And all what you are seeing is 5 of them in here. And if you zoom on one of these galaxies, that's what a typical galaxy would look like. And each galaxy actually has billions and billions of stars, in that galaxy. So just imagine this universe, around us, where literally you have billions of stars and billions of galaxies. And it turned out on many of the stars in those galaxies, actually there is a disk of dust which forms around them. So when the star collapses and creates a sun, like our sun, there is a disk of dust around them, and the particles in that dust accumulate together, and they form planets. And that's how our solar system formed. So these are the 8 planets in our solar system. Earth is that little blue dot, the third from the left, so you see how teeny we are. And this is an example of a typical solar system or planetary system that we are seeing. And then somehow, on one of those planets, which we call Earth, it had the right temperature, it had the right environment, that it led to organic molecules to form. And then after 4 billion years of evolution, we have the beautiful world that we live in. So the key question is, isn't that amazing? How did that start from those particles? And here today, you and I are sitting down having this conversation here. How did that form? How did the star form? How did the planet form? How did life start? Is life common? Is it across the whole universe? Or is it rare? Is it only in this place that here? There might be other New Zealands, across the universe, or other Wellington across the universe. So these are the kind of things we are trying to understand in our exploration. We are trying to do what I call writing the book about how did we start about, or how did we come about today? Are we the only people in the universe? Are we common? Is life common? Is life different, in other places than here? And these things are not going to happen overnight, by doing one mission. But we are doing step by step, learning about our solar system and the universe around us, so we can answer the question, are we alone, and how did we come about? So let me start by describing to you the planet which is the closest to us, and that's Mars. Mars has a lot of similarity to Earth and some differences. It's about 1/4 the size of Earth. So if you take the oceans away, Mars and the landmass on Earth are about the same size. So it's a big place. Mars has an atmosphere, much thinner than Earth, but it still has an atmosphere. If you look at it in more detail, you see on the right is a Grand Canyon on Mars. On the left is a Grand Canyon on Earth, which we have in the western US. They look very similar. If I didn't tell you the one on the right is a picture of Mars, you would have thought it's some area in the United States. And as you look in detail, the picture on the left is a detailed picture taken of the Grand Canyon on Earth, and you see those layers of sedimentary rocks. The picture on the right is the wall of a crater on Mars, and you see the layers in it. Now, layered rocks get geologists very excited. Now, I don't know how many geologists there is in the audience here, but that's how we learn about the history of that location. Because the top layer is the most recent. It was deposited recently, that means in the last few million years. The layer below it was a few million years earlier. The layer below it is a few million years earlier. So by analyzing the different layers, you are going back in time and learning about what happened in that location. What was the environment? What kind of vegetation grew in that environment? So by studying those layers on Mars, it will allow us to learn about the history of what actually happened on Mars and the similarity and different than with our planet. There are volcanoes on Earth, there are volcanoes on Mars. The picture on the left is a volcano in California. The picture on the right is the largest volcano on Mars. It's called Mount Olympus. It's twice the height of Mount Everest, so it's a huge volcano, but it's extinct today. So sometime in the past, there were a lot of volcanic activities on Mars, but somehow things changed and that volcanic activity stopped on that planet. This is a test I give to my student at the university. I tell them, guess which one is Mars and which one in the desert in California. You'll have no idea about the difference. Matter of fact, I forgot which one it is, after a while. I think the one to the right is Mars and the one to the left is in California. But the point of this is that Mars geologic activity is very similar to our planet. In the future, when we send the astronaut to Mars, she will think she is in California. That will be very similar to the environment that we have in here. But there are differences. So now let me tell you a little bit, before I tell you about the results that we have gotten, let me tell you about the challenge it takes to actually travel, to those planets. First, the distance. If I was driving my car at full speed, it will, day in, day out, it will take me 170 years to get to Mars. That's how far Mars is from us. When we send, Curiosity, after traveling 450 million kilometers, we had to land within a 2-kilometer circle, to be able to be successful in our landing. Let me give you an idea what that means. That means if I hit a golf ball from Los Angeles toward New Zealand, the golf ball has to come straight in the cup. That's how accurate we have to navigate. And to make it a little bit more challenging, the cup is moving, at very high speed, because Mars is moving and the Earth is moving. We're both moving. And we still have to navigate accurately enough to be able to land that spacecraft at the right location, at the right angle. Another example of the challenge is the energy with which we are coming, which we are arriving Mars. We're coming at a speed of 20,000 kilometers per hour. That means I can get back to Los Angeles in half an hour. And the amount of energy in that spacecraft is the equivalent of 18,000 race cars going at full speed. And we have only 7 minutes to dissipate that energy and land softly on the surface. That's why we call it the 7 minutes of terror. And that's the time from when we reach the top of the atmosphere until the time we land, on the surface. And I will show you in a little bit how the technique we use to do that. And finally, there was a challenge how at the end, you land on the surface, considering it has very little atmosphere. Here on Earth, you can come down on a parachute. And the parachute will slow you down enough that you can come down to the surface and not hurt yourself. Well, on Mars, there is not enough atmosphere to slow us down enough, at the end to land softly. So we had to come up with some ingenious ways of doing that. So when we landed Spirit and Opportunity 10 years ago, we used airbags. So just at the last few minutes, or matter of fact, 15 seconds, we fired retro rockets to slow us down. We inflated airbags around the lander, and then we let it bounce, on the surface. And once it stopped, we deflated the airbags, and that's how we landed safely. On Curiosity, the one we landed a year and a half ago, the rover is about the size of a car. So it was just too heavy, to be able to land it in airbags. So what we did, we actually fired retro rockets, hovered over the surface, and sky craned the rover down slowly to the surface so it gently touches the surface. Now, when we first described this technique to people outside JPL, they thought we were crazy. They thought we were smoking something in California, which is illegal, and we were going crazy about doing that. But when you sit down and think about it, it turned out the most elegant engineering approach to actually land on another planet. And it turned out we actually do it here on Earth. That's how, when you are transporting heavy equipment, you come with helicopters and you kind of hover over the surface and land them. The only difference, what we were doing is on another planet. And it has to be done all robotically. So what I'm going to do now, I'm going to show you a short video which basically shows you the challenge, in the words of the engineers who developed Curiosity, the challenge of building that rover, the tension that we were the expectation of it, what was happening in the mission operation room at JPL as we were landing, and what was happening across the United States. The night of the landing, there were 50 million Americans on our website, watching the landing, or at the museums, watching the landing, or at Times Square. The day after the landing, there was 1.5 billion hits on our website worldwide. People wanting to know what actually has happened. Now, some of these hits on the web were me checking every 5 minutes to see what's going on. But still, the number was a very large number. To tell you up front, what you will be seeing as we're approaching Mars, partly is animation, because we didn't have a camera sitting on Mars waiting for us, to arrive. But the animation was driven by engineering data. So it actually represents what happened. So what you are seeing is actually what was happening. And some of the images are actually cameras that we had on the lander taking pictures of the surface as we were landing. So actually you'll be seeing some animation, but actually some actual pictures. Same what we were watching, sitting down in the mission operation room, watching how things were happening. So let me... So the development was about 8 years, so we had to do a lot of testing, because once you launch a spacecraft, you cannot bring it home and do repairs on it. You're stuck with what you launched. So it has to work.
6, 5, 4, 3, 2, 1. Main engine start, 0, and lift off.
So that's a spacecraft separating from the launch vehicle. It takes about 9 months to get to Mars, with our spacecraft.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
Things are looking good. Coming up on entry. Vehicle reports entry interface. At this time, it'll begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. We are standing by for guided start of guided entry. We are beginning to feel the atmosphere as we go in here. The vehicle has just reported via tones that it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. We have seen peak deceleration. It is starting its first bank reversal. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Bank reversal 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Heat chill has separated where we found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending. Standing by for batch shell separation. We are in powered flight. We're at an altitude of 1 kilometer descending. Standing by for sky crane. Sky crane has started.
Signal to Odyssey, remain strong.
Touchdown confirmed. We're safe on Mars. Time to see where our curiosity will take us.
Not very often you see engineers crying.
got thumbnails.
Today, right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars. This is an amazing achievement.
Well, today on Mars, history was made on Earth. The successful landing of Curiosity marks what is really an unprecedented technological tour de force. It will stand as an American point of pride far into the future.
Well, tonight was a great drama that was played. I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things even though we might fail, than to stay in a twilight that knows neither victory nor defeat. Needless to say, as you could imagine, there was a lot of excitement and a lot of tension because for all the team that you see in there, these people have worked for 8 years, on this project. And it was one of the most challenging projects we have ever done. And there is no halfway of succeeding. It's either you're 100% successful or you're 100% fail. If the thing crashes on the surface, that's the end of 8 years of effort. If, on the other hand, success, even after a year and a half, every time anybody sees any one member of the team, they always congratulate them how exciting and how inspirational and so on. So these are the kind of business we see in space exploration. So now let me tell you what we've done. Of course, as soon as we landed, one of the first things we want to check that everything was fine. So we do exactly like what you do when you get a cell phone. First thing, you take a picture of yourself and send it to your mom. And tell mom, look, that's a selfie. So that's exactly what we did. So we took the arm of the rover has a camera on it. So we went and took a series of pictures from different directions. And then we cheated a little bit. We photoshopped the arm away from the picture here. So it doesn't look like you see you have an arm. So we spent the first few days actually checking that everything was working fine. And then we started exploring. Now, to tell you a little bit how we do this, we have a team of about 400 or 500 scientists from all around the world. And basically, they debate and discuss what are the measurements that we want to do. And then they reach a consensus on doing that. So every day, we send to the rover a series of commands of telling the rover, we want to do ABC. Like we see a rock there, it looks interesting, we want to go and drill in it. And then we go home. And then the rover, completely on itself, actually over the following 24 hours, does all the things that we told it to do, using a lot of its own artificial intelligence, because we cannot tell all the risks ahead of time. So as the rover drives, if you see like the surface is a little bit more sloped than we expected and it's a risk, the rover will stop and back off and try to find a different way of getting to that rock. If it cannot find a way, it stops and says, what do I do now? And waits until we come the following day, to tell it what to do. So it has a fair amount of intelligence, built into it. Now, after we landed, of course, there was a lot of popular things. So the media had, all kinds of cartoons about the thing. So it says, we followed me home, his name is Rover. But that was kind of exciting for us, but because it engaged the public, in a way. So it showed that the public is interested in the kind of things we do. And curiosity is becoming a common name, in the US, the same way as spirit and opportunity became a public, name. So one of the first things that we did is, as we were examining the rocks that we were seeing, we were very intrigued by looking at the picture to the left. That's a picture taken from the rover on Mars. The picture on the right, it's taken from what we call a conglomerate. What a conglomerate is for the non-geologist, if you look at the bottom of a river or a creek, you see a lot of rounded rocks, because the river tumbles the rocks and smooths it out, so they look smooth. And then if you put mud on top of it, you compact it. And after a few million years, that becomes a compacted, rounded rocks, within, basically mud on it, but hard mud. So that's an indication that that area was wet in the past. The picture to the left looked very similar to the picture to the right. If you examine those rocks, they are all mostly rounded, and they are compacted. So that gave us an indication as geologists that we landed effectively in a dry riverbed, an area where there was a river in the past, but basically it dried up at the present time. And this is a scene that's very close to where we actually landed. And again, if you examine it in detail, it looks like a dry lake. It looks like mud cracks, as the bottom of a lake. We have a lot of those lakes in Western California, in the desert in California, where actually you have lakes which evaporate. And then after a few million years, what you see is basically cracked mud, which is on the surface, very dried up. So we went into that area and started doing some sampling. So we took some of the sand that we have in there and put them in the instrument inside the rover, to examine them. And then we looked at some of the hard rock, and we did some drilling, in that rock. Now, I should tell you, on this rover, it's the equivalent of a chemistry lab at the university. It has X-ray machines on it, similar to when you go to the doctor and they take X-ray of you or X-ray of your teeth to really look at the detail. It has what we call mass spectrometer, which will allow us to analyze the material in the surface. It has ovens on it that we could put samples in those ovens and heat the ovens so we can see what's being emitted, so we know what gas is on the surface. So it's exactly like taking samples and you take them to a chemistry lab to figure out what those samples are made of. Now, once we started drilling in the surface, just the fact that the rock or the material which came out is gray instead of red was very exciting in itself. Now, you say, why was that exciting? Now, we all know Mars is called the red planet. And the reason it's called the red planet, because the surface looks very red. And the reason it looks red is because the oxygen in the atmosphere has oxidized the surface. So basically like rust. If you leave a metal, outside for a while, it gets that, rusty color. So one of the things we were concerned about is that rust and oxidation is not very good for a biological material. That's why you take antioxidant. Organic material does not like to live, in oxidized areas. So we were concerned of how deep is that oxidation layer and how deep do we have to drill to get to some fresh, material so we can examine it. So the fact that as we drilled, we start seeing this gray material told us that the oxidation layer is very, very thin. Matter of fact, it turned out to be a fraction of a centimeter. So then we took some of these samples, put them in the oven and the X-ray machine, and we started doing analysis. Now, I'm not going to go into the detail of the analysis, but let me give you the bottom line. Every element which is in your body actually exists on Mars. Oxygen, phosphorus, nitrogen, carbon, all the material which are the basic element on our planet which led to organic material and life actually exist on Mars. Now, we have not detected life on Mars. I just want to make sure that's clear. But we know that all the basic ingredients exist on Mars, and sometime in the past, there used to be oceans on Mars. So the next question is, if Mars was so similar to Earth 4 or 5 billion years ago, that there were oceans on it, there were all the material which led to life, could have life started on Mars? And if it did start, how much did it evolve? We know today it's very cold on Mars. It's much, much lower than 0 degrees. And therefore, we don't think there is life on Mars today. But clearly, sometime in the past, the fact that there were oceans, that means the temperature was pretty, pleasant to have a liquid ocean. And the immediate question, could have life evolved? And if it did, where it is? Did it evolve beyond a cell level? Can we find it, in the rock material that we have on Mars? So that's the next major objective, in our exploration. And then one of the other things that we did, we took some of the rocks and we dated those rocks. There is a technique on Earth here that we developed to see how old the rocks are. And what we found out, that the rocks on Mars are about 4.2 billion years old. That turned out to be about the same age as the rocks here on Earth. So that gave us an indication that Mars and Earth were formed roughly at the same time. And then on the left, you see what the rocks which are exposed on the surface, that turned out they have been exposed for about 80 million years. That means the rocks came from the bottom to the surface, through some tectonic or volcanic activity, and they have been sitting on the surface for about 80 million years, which is very similar to what we see here, also on Earth. So we started traveling. We traveled now about 5 kilometers. It doesn't sound a lot in 1 year, but when you are roving on another planet, that's a long distance. And about 3 weeks ago, we celebrated the 5 kilometer by having all the employees at JPL going and running for a 5K run. So we get a feel of what actually the rover actually has done. But to show you some illustration of some of the challenges we have as we are driving, this is an example of a sand dune which was in front of the rover about 3 weeks ago. And we had to figure out a way to drive over that sand dune so we go to the other side. So what I'm going to show you now is a very short video of the camera at the tail end of the rover. And you can see how the rover was actually going, over that sand dune. So it will take you as if you are sitting on the rover and watching the scene behind you. So that's a mountain where we landed. And you see now we went over the sand dune and we came. So it's going to replay again. And you can see the tracks, of the wheels that you have on the rover. And it's always a challenge because we don't know how soft or hard those sand dunes are. So we have to drive very carefully so we don't get stuck, in them. And the rover has enough intelligence that they can tell if it's spinning, the wheels are spinning, or if it's basically having traction, on the surface. And that's where we are heading. We will be getting there probably by about the June, July timeframe. And that's an area where you see all these layers, which are particularly interesting for us because these are the kind of areas that you find fossils in them. Now, again, I want to be careful not to tell you that we're expecting to see dinosaurs on Mars or anything of that nature. But what we call sedimentary layer is areas where you preserve organic material. On Earth, that tend to be places where organic material is preserved well in it because they tend to form at the bottom of lakes, and then you get multiple layers. So our plan is to drive up those hills and examine those different layers and do analysis of the different layers. And who knows what we'll find. We might not find anything, or we might find some really exciting things. And that's what exploration is about. If we knew what we were going to find, it wouldn't be exploration. So we will be surprised probably every day as we are doing those analysis and looking at the different materials in those rocks. Now, let me tell you about the future, what we're planning to do. We are already starting to plan of what to do in 2020 and beyond. So the next major step, we want to land rovers on Mars, go and look at the most interesting area based on the results of the present on Curiosity, collect samples, put them in a canister, and then send another lander which will land on the surface, grab that canister, put it on the top of a small rocket, and launch it to go in Mars orbit, and then have a spacecraft rendezvous with it and bring the samples back to Earth. So the idea is sometime in the mid-20s, we'll actually bring samples from Mars so we can do a lot more detailed analysis with them, and that will prepare for sending humans in the 2030 timeframe. That will tell us a lot more about Mars, what's interesting, what's not interesting, is the material toxic or not toxic, how do we design space suits, to protect the astronauts, from the environment on Mars, or do we need, to do that? So that's kind of our next 20 years, plan. So during the lifetime of many of you, definitely the young ones here, actually you'll be seeing astronauts traveling and coming back. Now, let me tell you about some other thing. I mean, Mars was the key thing I wanted to describe to you here, but the solar system has amazing diversity in it. The other very exciting one is Saturn. And we have a spacecraft in orbit around Saturn as we speak, which is called Cassini, which have been for 7 years now exploring Saturn. Now, Saturn is interesting because it looks pretty and it has the rings around it, but there is more reason scientifically why it's interesting. Those rings, around Saturn, they look like they are solid sheet, but in actuality, they are dust, particles of dust, which are all lined up, in a flat plane, which is going around the planet, in a similar way of what I told you at the beginning of my talk, that disk of dust which led to the formation of our solar system. And you see gap in that disk, and that's where actually particles have been swept and they formed small satellites. Now, to believe me, this is a picture of the satellites which are around those rings. So Saturn is like a mini solar system. So it's basically a solar system forming in front of our eyes. And we will, as we watching it, we'll see how, on a slow basis, how those satellites are actually forming. And it turned out a couple of those satellites are particularly interesting. There is one satellite called Titan. That satellite is bigger than our moon. It has an atmosphere, the same pressure as the atmosphere here on Earth. It has rain, it has clouds. You see in the middle, it has rivers and what looks like ocean. On the right-hand side are lakes, which actually exist today. So it has rain, it has lakes, it evaporates, goes in the atmosphere, exactly like what happens in New Zealand, except it's not made of water, because Titan is so cold that the water will be frozen. And all this liquid is basically hydrocarbon. So it's like gasoline in your car. So if you're living on Titan, you don't have to go to a gas station. You go to the nearest river, take a bucket and fill it up with gasoline and put it in your car. On the other hand, if you light a cigarette, the whole planet will blow up in one big boom. But the point, the reason scientifically it's interesting, this is a planet which has basically organic material, because hydrocarbon are organic material, but it's too cold for life to have started. So some people believe this might be what our planet looked like before biology got started. And that on Titan, because it's so cold, it's like it's in a freezer. And it will give us a picture of our planet a few billion years ago before life actually started. At least that's one theory. And that's one of the areas that we're planning another mission to actually send balloons, boats to go into those lakes. So that will be the next generation of exploration that we'll be doing of that planet. Another exciting place is also a satellite of Saturn called Enceladus. Now that satellite is much smaller. It's about a couple hundred kilometers in size. We know it's made of ice, water ice, because we can measure the surface, what it's made of. But what's amazing, we see geysers shooting out of that ice. You see it at the bottom. These are geysers which are about 50 kilometers high. So it's really shooting, like I guess in the northern part of the island here, you have an area where you have the hot water and you have geysers which are shooting, but they go 50 kilometers up in the sky. So we flew the spacecraft through the plume of those geysers, and they are made of water. And basically we believe that what's happening on Enceladus, that there is an ocean just below that ice layer, and as Enceladus goes around Saturn, and it has tides, like what happened, the moon has tides, create tides on Earth, it's pumping, that satellite, and the heat is actually shooting geysers, from it. So then the next question is, if there is an ocean, and if it's a liquid ocean, could life has evolved, in that ocean? So that's one of the other missions we are thinking about sending. And now this, I think, is a particularly interesting picture because it puts all of us into perspective. About 3 months ago or 4 months ago, the spacecraft was just behind Saturn relative to the sun. So the sun actually blocked Saturn, Saturn blocked the sun. So basically that allowed us to see very faint object around Saturn. Because like when you walk into a bright room and you have a bright light, so you have to put your hand to block the light so I can see your faces on it. So that's what we did. And you see that little bright dot to the bottom right? If I expand it, that's us. That little dot is Earth. And the dot next to it, that's the moon. So that little dot is all of you. All our friends, all the people we like, all the people we don't like, they all live on that little dot. So that will give us a perspective of our place, in the universe, how small, our beautiful planet is. So let me move and tell you a little bit about some of the other exciting places in our universe. This is Europa, a satellite of Jupiter, not of Saturn, but of Jupiter. But you can look at that surface. It looks very much like when you fly over the North Pole. It looks like floating ice and cracks, of the ice. And on top of that, we see this orange material, which looks like organic material. So Europa also, we believe, is similar to Enceladus. It's a planet which is the size of our moon, where there might be an ocean below the surface. There is a thin layer of ice on top of it, and there are cracks which are in that ice, and we are seeing potentially organic material seeping out from that ocean. So we are in the early stage of planning now a mission to go to Europa, where what we want to do, we want to sound that ice, see how thick it is, in areas where it is thin, actually drop a lander, melt our way through that ice to the ocean, and see if we can have a submarine, if we can see if there is life in that ocean. So that's the kind of mission we're planning as we speak today, that we're thinking of launching in the 2020, 2021 time frame. So that will be equally exciting, depending what we discover, than what we have been doing on Mars. And that's, let me skip that one. Now, the other thing we are doing, as we speak also, we have a spacecraft which have visited Vesta. Vesta is the second largest asteroid. This asteroid is bigger than New Zealand, about 4 or 5 times the size of New Zealand. And that's what we call an early planet formation. That means that's likely what our planet looked like before it became as big as it is today. And then after we are done with Vesta, which we just left a few months ago, we're going to Ceres, which is the next largest asteroid. It's the largest in the solar system, which is the size of your neighboring island of Australia. And that will give us a picture of a basically planet which is a little bit bigger. So by looking at these different objects, it will tell us how our planet was built and how it became about where we are today. Now, the other step we are looking at is, then the next question is, are there other solar systems? Like our solar system. Do other stars have planets around them? So about a few years ago, we launched a satellite. And what we did with it, it's a telescope which looks at stars and measures their brightness very, very carefully and see if every once in a while there is a blip, in their light. And then if that blip is periodic, that means there is a planet which comes in front of it and blocks a little bit of the light, so that decreases the light a little bit. And if it's periodic, that means there is an object which is going around the star. What we found out is that there are literally thousands and thousands of planets. Almost every star has multiple planets around it. So when we think we are unique, we are not. All the stars around us actually have planets which are around them. Now, we have not taken images yet. That's the next step we want to do. The next step we want to do is like we showed you on Saturn. We want to have a telescope which will block the light of the star so we can see the little planets which are sitting next to them. And then from that, we can start taking pictures. From that, we can determine what's the temperature. Are there clouds? Are there oceans? Is there oxygen in the atmosphere? And by going through those steps, we can determine if there are planets similar to Earth. So that's the kind of things that we will be able to do literally within the next decade. So if you invite me 10 years from now to come and give a lecture here, I will show you the family portrait of the neighboring few solar system around us. Most likely it'll be one of the younger people here who will be doing that. So now let me finish by giving you a couple of examples of how we're applying some of that knowledge and technology to our own planet. So this is an example of one mission that we have, which we call GRACE. And what we are doing here, we're measuring very accurately the gravity field of our planet. Now you say, well, the gravity field is fixed. We know, our weight is fixed unless you are on a diet, so that doesn't change. Well, it turned out actually the gravity field does change. In the winter, when there is rain in the Amazon, there is a lot of water which comes in the Amazon basin, so you have more mass. In the summer, all that water goes into the ocean, so you have less mass, in the Amazon. So what you are seeing here, we're measuring the amount of water which actually went into the Amazon basin, and over the year, how much of it is going into the ocean by measuring the mass of the surface or the gravity field. Many of you heard that we think that Antarctica and Greenland are actually losing their ice. That's how we measure it. We measure the gravity field from space. We can determine the amount of mass which is in Greenland, and by monitoring it, we can determine how much ice is being lost, to the ocean, and you can see it in the picture here. It shows you the change in the mass over the last 20 years in Greenland. In a complement to that, we say, where is that ice going? It's going into the ocean, and we have been measuring the height of the ocean for the last 20 years, and the height of the ocean is rising. It's rising a few millimeters per year. So if you live very close to the coast, 50, 60 years from now, you can see the ocean basically will be about 1 meter or 2 meters, higher. And that's a result of the global warming which is happening on our planet. And that's why it's very important that we understand what's happening to our environment and be able to mitigate it. Either figure out a way to reduce that global warming or get adapted to the changes which are happening in our environment. So when you hear people saying there is changes in our climate, the ocean is rising, and the ice is melting, and we are losing ice in Antarctica and Greenland, these are actual facts. Now, you can debate if it's humans which are leading to that or not. That's a different debate. But the fact is that the environment is actually changing, and it's very likely humans are playing an important role in that happening. Now, let me show you one other example, which is very important for you here in New Zealand, very important for us in California, is technologies that we have adapted from some of our space mission to actually measure fraction of inches of motions in the surface. Now you say, why is that important? That's what happened around the edge of plates. And as the plates try to move, they actually create stress. And by measuring the changes in the surface of the plate, it will tell us which area are high risk of earthquakes actually happening. So with this technology, we will be able in the future to say, this area seems there is a lot of stress because we see a lot of bending, which is happening like you see along the coast of South America. And therefore, there is a high likelihood of an earthquake happening in that location, or that location is more safe, and therefore the likelihood is much less for that to happen. So that's an example of the kind of application that the space program is bringing to our day-to-day kind of life. Another example, which is probably more directly relevant to many of you, all of you have cell phones. I'm pretty sure all of you have cell phones. The code that is used on those cell phones were developed 30 years ago at JPL to communicate with our spacecraft. And then some entrepreneurs picked that idea and use that technology to actually develop cell phones. The camera in your cell phone, the focal plane of that camera was developed for our telescopes to actually take images, very sensitive images of the stars. And an entrepreneur picked that, and that's how it ended in your cell phone. I understand that here you have computer graphic is very important, business in here. Computer graphics started 20 years ago. There was a researcher at JPL by name of Jim Blenn. You can go and Google him. And he wanted to figure out, how do we visualize when Voyager was flying by Jupiter? How do we visualize where the sun is? What's the reflection, on Jupiter? Where should we point the camera as the spacecraft is moving? And he basically started the foundation of computer graphics, having no idea that it's going to be a big movie business, in New Zealand. But these give you examples of some of the technology that get advanced by doing space exploration. And then entrepreneurs pick up those ideas and that technology and develop it, and use it. And the last example I want to give you, I didn't mention it, on that rover, there was an arm, that were used to do the drilling and the sampling. Well, that same technology is now used by surgeons to do remote surgery. So when you see an arm in a surgeon, room, doing the remote operation, it's all based on that kind, of technology. So let me end my presentation with this picture. For me, this is probably the most iconic picture. The picture to the left is the footprint of Neil Armstrong on the moon. I was roughly the age of some of the young people. It was my first year, at the university, and I was amazed that actually we can land on another planet and actually see our footprint, on the moon. The picture to the right, that the footprint of the wheel of the rover on Mars. So hopefully that for the young people here, that will inspire you that actually we can go to other planets. And this is our footprint. It's our robot, but it's our footprint on another planet, and anything, is possible for us to achieve. So hopefully you enjoyed, the big quick sweep about what's happening in our solar system. And I want to go back and give credit to Sir Bill Pickering, who was born here in Wellington and came to the US to be one of the founders of space exploration. Thank you very much.